Record on. All right, welcome back. Good morning, everyone. So we're going to start our lecture series with Wang Wang from East China Normal University. Wang is going to tell us about Dirac operators and representation theory. Wang, please.
Thank you for the introduction. Today I'm going to introduce you something about Dirac induction in this series of lectures. And today's lecture is only about Dirac operators. And today's topic is about, first of all, a general introduction on what is a Dirac operator, and then something about its relationship with representation theory, which is brave. And then I'm going to talk about generalized Fredholm index of a Dirac operator, that is some index in K-theory of the reduced group system algebra. And lastly, I'm going to briefly introduce what is a Dirac induction. And in the next two lectures, in the second lecture, I'm going to introduce the isomorphism of Dirac induction, which is known as the Kasparov isomorphism, and some history about that. And in the last lecture, I'm going to show you a proof using Fourier transform. So let us start from the definition of a Dirac operator. So first of all, I would like to start from Dirac type operators. So let us consider a Riemannian manifold and a Hermitian vector bundle S over that manifold where an inner product is specified. And let us consider the set of compactly supported smooth functions, which is denoted by C infinity sub CMS. And the Dirac type operator is a symmetric first order elliptic differential operator satisfying the following identity. The identity says that the commutator of this first order elliptic differential operator with a smooth compactly supported function on M, the square of that is equal to the minus of the norm of the differential of this function. So this last equality can be thought as a replacement of the differential of a function by the commutator of a function with this operator. And this appears a lot.
Excuse me, Han, do you want the square on the left, or is that correct? Or?
There is a square on the left.
Okay, just checking, thank you. So it's the square of the commutator, okay.
Yeah, the square of the commutator. So in principle, I just want to comment that this commutator is a replacement of the differential in the non-commutative geometry context, where in the notion of a spectral triple by Alan Kahn, that is to use the commutator of a function with a Dirac operator to define a distance, of two elements on the so-called on the spectral triple. And one can also see this notation, the commutator D and F in the quantized calculus in non-commutative geometry. So in that quantized calculus, all the differentials are replaced by this commutator, and the integration is replaced by the Dix-Smear trace. So I used this non-technical definition to show you this is the Dirac type operator. And let us see some examples. So the first example I'm showing you is an operator on R3, where is an operator on R3, and it has coefficient in 2x2 matrices, and in front of ddx, ddx x1, x2, and x3, we have the Pauli matrices as follows. And it turns out that one can check this operator satisfy the conditions in the previous page. That is, D is a symmetric and first order differential operator. These are very explicitly, these are very simple to check. And we can also check the commutator. The square of the commutator is the minus of the norm of df. By doing this calculation, one see that the commutator is just to take the partial derivative of f with coefficient in sigma I. And one can take square of that operator and obtain this sum. And one can check that these three Pauli matrices, they satisfy this condition, sigma I, sigma j plus sigma j, sigma I is equal to minus 2 delta ij. That means when I is not equal to j, the term vanishes, and when I is equal to j, it contributes to minus 2. And from that, one can check that the equality is satisfied. Maybe I made a mistake here. Oh no, there's no mistake. So this is a Dirac type operator from the definition above. So I think there is another line, but cannot see it. Okay. So let's see some other examples. So this example is an oriented Riemannian manifold M, and let us consider the bundle to be the exterior algebra bundle over this manifold. Consider the de Rham operator. Consider the de Rham operator on M, which is defined by taking the exterior derivative plus its adjoint with respect to the an inner product specified by the Hodge-Star operator, and one can specify a Z2 grading on this exterior algebra by the parity of the forms, and then one can consider this de Rham operator on this vector space, and this is also a Dirac type operator. And another similar Dirac type operator is the so-called signature operator. Basically, it is the same de Rham operator, but with respect to a different grading, which I'm going to omit. It is some grading specified by the positive and negative eigenspace of the Hodge-Star operator. With respect to that grading, it is called the signature operator, which is also Dirac type. And a last operator I'm going to mention is the double operator. It is to consider a complex manifold and consider the holomorphic forms and the anti-holomorphic forms. And when only restricted to the anti-holomorphic forms, that is when you have PQ forms, when only consider the case where P is equal to 0, and consider this D bar operator plus its adjoint, and that is known as the double operator, Cauchy-Riemann operator. That is also a case of Dirac type operator. So knowing these Dirac type operators, one can also use a Dirac type operator to produce another Dirac type operator by giving another vector bundle V. So given another vector bundle V, one can always define the so-called twisted Dirac operator by compressing this vector bundle to this operator. So the compression works like this. So because we have the Sayre's 1 theorem, so a vector bundle can be a direct summand of a free the sections of a vector bundle can be regarded as a direct summand of a free module. And from that free module, one can produce a projection. And on that free module, one can produce this diagonal operator, just act by the original Dirac operator and compressed by these projections. It turns out this is also a Dirac type operator. Of course, when we use the definitions of connections in defining the Dirac type operator, one don't have to define it like this, but in this way, one can still show it is a Dirac type operator. And now we want to ask one thing. First of all, we remark that all Dirac type operator it is acting on some bundle, and it is an observation that this vector bundle has the dimension that can be divided by some power of the two, and this power of two is simply depending on the dimension. So if the dimension of this manifold M is even or odd, let's say 2k plus 1 or 2k, then this dimension M over 2 is just taking the floor function is just k. This is 2 to the k always divides the dimension of this S. That is an observation. And because of that, any Dirac type operator, when you see locally, it is some canonical Dirac operator twisted by a vector bundle. So by canonical, I mean that it is an operator. It is a Dirac type operator where S has the minimal dimension. But in the next few slides, I'm going to make it precise. We have to introduce the Clifford algebra. So by saying CLN is a Clifford algebra, we say that it is a map going from Rn to so the notion of the, sorry about this. I don't know how to. Okay, and the notion of the Clifford algebra is trying to define a multiplication of vectors in Rn. So we say a Clifford algebra is an algebra generated by an orthonormal basis EI for Rn, where each EI is corresponding to some elements in this algebra satisfying this condition. This condition is the same as the condition that is satisfied the Pauli matrix in dimension 3. And using this, one can talk about the canonical Dirac operator and on Rn. The canonical Dirac operator on Rn is simply defined as a first order differential operator whose square is the Laplacian. And when you calculate, when you solve the equation that d squared is the Laplacian, this Clifford algebra condition is naturally satisfied. And actually, one can find a matrix representative of the Clifford algebra. In fact, for n equals to 2k, even case, the Clifford algebra can be isomorphic to a matrix algebra. And this matrix algebra is a 2 to the k by 2 to the k matrix. And in the odd case, it is a direct sum of two matrix algebras of the rank 2 to the k. And one can easily check that in this case, if we use this matrix representation of the Clifford algebra, one can check that these Dirac operators on Rn is actually acting on c to the 2k. And one can check that is the minimal one can achieve. So this is the canonical Dirac operator we would like to have. And then we would like to ask, is that possible that all canonical, any for any manifold, we can have a canonical Dirac operator on it. And the answer is not, unless we can give a topological condition on the manifold that is known as the okay, the problem is that I cannot see the title of each page, but I hope it doesn't bother you. Anyway, so this page is about spin C and the spin structure. So we would like to give a topological condition on the remaining manifold so that a canonical Dirac operator can be defined. So to introduce that, one need to first note that, sorry about that. First note that the fundamental group of SON when n is larger than 3 is Z2, and when n is equal to 2, it is Z. So for any n SON admits a double cover, and we call that a spin group. And we also can define the so-called spin C group by associating a U1 group by doing this balanced product as spin n times U1 over Z2, where Z2 is acting on the spin by the covering group, and on U1 by just folding the circle. And we say that oriented Riemannian manifold admits a spin or spin C structure if the transition function admits a lift from SON to spin or spin C. This Riemannian manifold Riemannian and orientation condition guarantees that one can always adjust the transition function to take coefficient to take values in SON. This transition function may not always lift to this spin C or spin group, but if it can have a lift so that the cocycle condition are satisfied, then it is called the M has a spin or spin C structure. This cocycle condition just means that after this lift, one can still glue the local sections into a vector bundle. So in general, if you don't have this condition, it can be if you don't have this cocycle condition, you can of course always have a lift, but without this condition, one cannot gluing it again using this new structure group. This condition also means that one can consider there's an equivalence definition of the spin or spin C structure. That is, one can view this tangent space one can view this tangent space of M as an associated bundle of some principal SON bundle. And if this principal bundle admits a double cover of some principal spin N bundle, then it is said to have a spin structure. But I didn't use that equivalent definition. So let us see some examples. So if M is a complex manifold, then it can be checked that M has spin C structure. And we know that complex manifold is always orientable. Actually, spin C condition is a spin C condition is a little bit stronger than orientability, and it is known as the K orientation, which means that if M is if a Riemannian manifold has spin C structure, then one has the so-called K theoretic Bancali duality. That is there is an isomorphism between the K theory group of manifold and the dual theory group which is known as the K homology. Remember that the canonical Pankali duality requires that M to have orientability so that the homology and cohomology can be isomorphic. And here we have the homology and cohomology on K-theory level to be isomorphic, and that requires the spin C condition. And with this spin C or spin structure, one can define the Dirac operator. But before that, we have to introduce the notion of spinor bundle. That is the minimal dimension condition. So that is the smallest bundle that a Dirac type operator can act on. So if one has a spin C structure of even dimension, then one can always find a spinor bundle. And actually, I just stated, but to show that when one needs just to lift a principal SON bundle to the principal spin bundle and using the spin representation to recover this associate bundle. In any case, as long as M has spin C structure, one can construct by spin representation a spinor bundle of the correct dimension. And moreover, one can find isomorphism of algebras going from the Clifford algebra bundle to the andromorphism of the spinor bundle. So this Clifford algebra bundle is just to think of the tangent bundle, Tm. You think of at each point, it is a tangent space, which is viewed as an Euclidean space, and you find its Clifford algebra. And letting this X change continuously, one can have this Clifford algebra bundle. And note that for the Clifford algebra bundle, we have the, so note that we create Clifford algebra in order to define multiplication of vectors in Rn. And in this case, we would like to define multiplications of vectors or covectors on M. So actually, this isomorphism specify module structure of S for Tm. So that means for any element on the spinor bundle, the covector or vector of M can act on this vector bundle using under this isomorphism. And this isomorphism is known as the Clifford multiplication. And a spinor bundle actually satisfy further conditions, which I'm going to recall briefly. A spinor bundle has the property that one can define a Hermitian metric on it, which means that the Clifford multiplication appears to be a skew symmetric operator on this spinor bundle. And also it carries a connection, a spinor connection, nabla S, which is compatible with the Levi-Civita connection. And the compatibility is in this sense, when we have a multiplication given by multiplication of Tm of a vector or covector on a spinor bundle, the Leibniz rule of this connection will have to be satisfied, and that is the compatibility of spinor connection and the Levi-Civita connection. And with these two extra conditions, one can finally define the official Dirac operator. So if M is a Riemannian manifold with a spin or spin C structure, and S be the spinor bundle. So that is the smallest possible dimension bundle that Clifford algebra can act on. So the Dirac operator is then given by taking the Clifford connection with respect to a local orthonormal basis and multiplied by this Clifford multiplication specified in this isomorphism. And this is the Dirac operator. And one can see that in the case of Rn, this nabla is just replaced by the directional partial derivative, and this CEI is just some matrix. But in general, we won't have a constant EI in the general case of a manifold. So this is the definition of the Dirac operator. And one can further check with this very precise definition that D satisfies the condition I specified for Dirac type operator on the first slide. That is, it is formally self-joint, first order differential, and satisfy this condition. And one thing I would like to mention is that when M has even dimension, the canonical Dirac operator is of this off-diagonal form, and we call that form as odd type. And because D is formally self-adjoint with respect to this Z2 grading of the spinor bundle, one can have D plus and D minus, which are adjoint to each other. That is something we will mention later. So another two examples of Dirac twisted Dirac operator is I want to reflect on the comment I said about locally all Dirac type operators are just canonical Dirac operator twisted by a bundle. So so we want to mention these examples of the Ram operator again. So if M is a oriented Riemannian manifold with a spin C structure, then if we take the spinor bundle, which is the bundle with minimal dimension, then because of the definition that endomorphism of S is the Clifford algebra bundle of Tm, and this Clifford algebra bundle is isomorphic as a vector space to the exterior algebra bundle of M. And therefore, one can ask, how does the Dirac operator, how does the canonical Dirac operator relate with the Ram operator? And that is, the canonical Dirac operator is, if you twist that by the spinor bundle, then it will be the Ram operator. And another example of the canonical Dirac operator is the double operator on complex manifold. I do this example, the reason is that this is very explicit because the definition of Dirac operator is quite complicated with this spin C condition. But if the manifold is complex, then it automatically has a spin C structure, and one can choose the spinor bundle to be the anti-holomorphic forms, the section generated by the anti-holomorphic forms, and in this case, the double operator can be identified with the canonical Dirac operator. And this is an example one can very precise example of a canonical Dirac operator. Okay, so that is the first part of my lecture. Now I'm going to say a few words about representations and Dirac operators, but very briefly. So, so Dirac operators appears to be a very important geometric tool in representation theory, starting from Borel, Wei, and Bott. They gave a geometric realization of a connected compact Lie group, the representation of connected compact Lie group by working on a twisted Dirac operator. So in principle, they work on the space, homogeneous space defined by the Lie group G over the maximal torus, and create a holomorphic line bundle over that, and consider the double operator, which is just the Dirac operator, twisted with that holomorphic line bundle, and the kernel of that operator realize the representation of irreducible representations of connected compact Lie group. Okay, and after Harris-Chandler have the classification of discrete series representations for semi-simple Lie groups, one has more analogous result as the Bray-Bott theorem generalized to the non-compact group. And I'm going to give the example of Parsasarathi and Atiyah Schmidt. So they also construct some geometric operators on the homogeneous space. And this time, the homogeneous space is non-compact, consisting of the semi-simple Lie group G divided by a maximal compact subgroup. And one can twist a K representation to create a homogeneous vector bundle over this space, and consider the canonical Dirac operator on this space twisted with that bundle, with that vector bundle, homogeneous vector bundle coming from the representation of K, and take the kernel of this operator to construct discrete series. This idea is integrated in algebraic language by introducing Dirac cohomology by Vaughan. And my series of lectures is going to be about a K-theoretic version of Dirac operators, describing the Dirac operators in the K-theory context, known as the Kohn-Kasparov isomorphism. And that isomorphism is to use something called Dirac induction to calculate the K-theory of the reduced group system algebra via some index of some Dirac operator. I'm going to talk in precise about this aspect in the next two lectures, so I'm going to skip this. Okay, so now I'm going to describe how does the Dirac operator on the space that is related to representation works out. So here in the context here, we have a real or complex semi-simple Lie group G and a maximal compact subgroup. And the manifold we are going to considering is the homogeneous space G mod K. And to study representation theory of G in relation to operators on this space, one need to have some geometric operators like Dirac operators to do it, and one need to have a Riemannian manifold structure. Unfortunately, we have. So we consider the Cartan decomposition of the Lie algebra of G into the Lie algebra of K and the P, which is a complement given by the structure of the Lie algebra. And this P actually can be identified with as the tangent space at the identity in this G mod K identity element, which I call X0. So this P can be identified as the tangent space at X0 of this G mod K. And actually, this is very natural to think about this because P is supposed to be the Lie algebra of something, and the Lie algebra means taking the tangent space identity, and this is indeed satisfying this kind of analogy. So this is quite obvious. And the Killing form on this Lie algebra gives rise to a K-invariant inner product on P. The Killing form does not always give a positive definite product on G, but when restricted to P, it is an inner product. And this gives us a Riemannian manifold with a G-invariant metric for this homogeneous space. And with this Riemannian manifold structure, one can talk about Dirac operators. But again, we have to say again the technicality about the spin structure. So recall that spin structure has something to do with lifting to the double cover. And here we have the same kind of requirement. We say that this homogeneous space M has a G equivariant spin structure. If the adjoint action of K on SOV. So there is an action of this compact group K on V by adjoint, and one can check this is this lensing SOV. It's orthogonal, special orthogonal, and we say that this manifold has a G equivariant spin structure if this adjoint map can be lifted to the double cover. So this is very similar to the original definition, because previously we have lift from SON to spin N, because previously from a Riemannian manifold, the structure group is SON, but here the structure group is K, but we represent it as into SON, and we can still do the same definition and make it work. In any case, with this technical condition, one can define the Dirac operator on G mod K. And I want to say an example. How do we usually avoid talking about this? One can always consider a double covering. So this is here is an example. So if G is SL2R and K is the maximal compact, which is SO2, then when see that the G mod K is identified with the hyperbolic plane, the complex plane, upper complex plane, and since both the fundamental group of SO2 and SL2R are Z, so they have a double cover, and fortunately, the double cover are also groups. So we can take the double covers of those GK as groups, and we can form the quotient, which is still M. But with this double cover, one can always talk about G equivariant, G tilde equivariant spin structure. So by passing to a double cover, one can always avoid saying this G equivariant spin structure. So although it looks complicated, but one can avoid it. And in fact, I'm going to always assume G equivariant spin structure in my rest of the lectures. Okay, so now I'm going to talk about what is the Dirac operator when we have a G equivariant spin structure. So if we have a G equivariant structure, then we can form an associate bundle, just like forming the spin bundle. So recall that the spin bundle is formed by lifting a principal SON bundle to principal spin N bundle. And by associating a spin N representation, irreducible representation of spin N. Here we can do something similar. We can also think about an irreducible representation of this spin group, and we can do some association like that to obtain a vector bundle G over K. That is going to be our spinor bundle. And with this representation, one can also obtain an isomorphism given by the Clifford algebra multiplication. So this P is playing the role of Tm previously, because M here is a homogeneous bundle. M is a homogeneous space. So all the tangent space of Tm can be translated from Tx0, which is V and which is identified as P. And in this fashion, that we can view this CLP the same as CL of Tx0m. So in a similar fashion, we can have an isomorphism going from the Clifford algebra of P to the endomorphism of this spinor representation, and that is an isomorphism. And the Dirac operator is given by taking the sum of CPI PI, where PI is an orthonormal basis of this P. So this PI is playing the role of a partial derivative, because PI lives in the Lie algebra, and Lie algebra one can use Lie algebra to define partial derivatives on the manifold. And also, because we identify Tm and Tm star, so this also linked to dxi. So this is essentially the true Dirac operator if one has the right spin structure on the manifold. So it is the true Dirac operator in the following sense. One can always think of this K equivariant part of continuous function on G tensor, this spin P representation delta. And one can think of that as the section of induced representation of delta, because delta is a representation of K, because there is a map going from K to spin N, spin V, and V is identified with P, and P is P represent on delta. So delta is a K representation, and one can induce this representation to G. And it turns out the sections of this induced representation is just this space. And this space can also be identified with the smooth, compactly supported function on the homogeneous space with values in this spinor bundle created by associating a spinor representation. And under this identification, one can check this definition of Dirac operator is the same as the Dirac operator defined using the connections and Clifford multiplications. On this slide, I'm going to mention a technical result about the square of Dirac operator. It is not going to be used today, but it will be used in the third lecture. So a precise calculation of the square of the Dirac operator of K. So we need some preparation about this. So the Dirac operator we are considering is the canonical Dirac operator D on G mod K, just as defined on the previous page, twisted by a K representation. So this V is a representation of K, and this representation of K we can produce a homogeneous vector bundle like this, and we can twist the canonical Dirac operator with this vector bundle to create this twisted Dirac operator, and it turns out it is acting on this K-invariant space. Okay, and we would like to find a formula for the square of this Dirac operator. And to state the formula, one need to label this. One need to label this irreducible representation of K by the highest weight, tau. And also one need to define the so-called Casimir operator on G. That is some element lies in the centralizer of the enveloping algebra of the Lie algebra G. So with these two notations, we can talk about the square of this twisted Dirac operator. And the square of the twisted Dirac operator is simply given by the minus of the Casimir operator plus the inner product of tau plus 2 rho K with tau, and inner product of rho with itself, and plus the inner product of rho K with itself. And here we have two other notations, rho and rho K. They stand for the half sum of positive roots. So one of that, rho K, is half sum of compact positive root. The other is half sum of compact positive root plus the non-compact positive roots. So so rho is a sum of rho K plus the non-compact half sum of non-compact positive roots. And we will leave this to later when we show Dirac operator D restricted to D. This dV is invertible using this formula. The invertibility, as we will see later, is very important because it means that the operator has 0 index in K theory. So we can tell by saying a Dirac operator is invertible or not by looking at its index in K theory is 0 or not. That is what we are going to say for the next few slides, the so-called generalized Fredholm index for Dirac operators. So let us first consider the case when M is closed. So here we assume a nice complete Riemannian manifold and a Dirac type operator. Recall that the completeness will ensure that the Dirac operator is not only symmetric, but also essentially self-adjoint. And with this condition, one can do functional calculus. And another condition that can be implied by Dirac operator is that it is an elliptic operator. And ellipticity is some condition saying that the principal symbol of that operator is invertible when outside 0 sections. And the principal symbol is defined by freezing the coefficient of the differential operator and taking the Fourier transform of the partial derivatives. In any case, for Dirac operators, which is for, let's say, Rn, if one want to find the principal symbol of that operator, it will just be freezing the coefficient, so the coefficient does not change, and taking the Fourier transform. And one can use the fact that C being linear to say that this is just IC psi. So one can check that this is invertible because C psi squared, because C psi squared is minus. So one can see that when this psi is non-zero, this is invertible. So in any case, Dirac operator is elliptic, And with this condition, one can say that this operator is Fredholm when the manifold is closed, which means it's a compact manifold without boundary. And for Fredholm operator, a very nice property is that this kind of operator has an index, which is given by, so the Fredholm index was defined by taking the dimension of the kernel and the dimension of the co-kernel, and take the difference. But here we are actually considering an even case. So we are considering an even manifold case where we only view the plus part of the operator. So the kernel of this operator is this one, and the co-kernel of D plus is just kernel of D minus, and this is defined as the Fredholm index of D. We don't take kernel D minus co-kernel D. The reason is that D is self-adjoint. We have to take half of that to be able to get a non-zero number. In any case, this is the Fredholm index, and the Fredholm index is a quantity telling you how far this operator is being invertible. Because if D is invertible, then it means that this number is 0. So if this number index is non-zero, then it means D is not invertible. And the next, I'm going to define another thing called K-theoretic index. So that is some index living in K-theory. And I'm going to show that K-theoretic index coincide with the Fredholm index. And to be able to define the K-theoretic index, we need to use the fact that D is essentially self-adjoint. So one can take functional calculus for D. So using the fact that M is closed, one can show that for a compact, for a function which is continuous and vanishing at infinity, the functional calculus of this Dirac operator is going to lie inside compact operators, and that can be extended to the multipliers. So in any case, one can use that to define a K-theoretic index in the following sense. So one can choose a odd increasing function like this, going from -1 to 1. And this function will have the property that chi² -1 belongs to C0R. And applying functional calculus to D, one can show that this operator chi D² minus identity is compact, while chi D is bounded. And this means that chi D is a unitary, is an invertible operator inside the quotient known as the Calkin algebra. So this chi D is invertible in this quotient. And because of that, one can view this chi D as an element in K1 of this quotient algebra and apply the boundary map of the 6-term exact sequence associated to this compact, bounded, and Calkin algebra and short exact sequence. One has a 6-term K-theoretic exact sequence, and using the connecting map, one can show that taking the boundary map, one can show that this element lands in K0 of compact operator, and that is isomorphic to Z. And when define this boundary map applied to the functional calculus normalization of D to be the K-theoretic index, it turns out that this K-theoretic index is exactly the K-theoretic index. But the good thing about that K-theoretic index is that this can be generalized to the setting to some non-compact setting. in the non-compact setting, the Fredholmness may not make sense. So in the non-compact setting, so if now we assume we have a complete Riemannian manifold and a Dirac type operator, which is essentially self-adjoint because of the completeness, one can always take the functional calculus. But in this case, D is not necessarily Fredholm, because if this manifold is not compact, and the image may not land in compact operators. However, when we have a locally compact group acting on this manifold nicely, which is some condition, proper co-compact and asymmetric condition, one can show that this we can still have a generalized Fredholm operator on some Hilbert module over some algebra. So one can think of this. So that means one can partition this space into a family that on each family D is each fiber of the family D is a Fredholm operator. So it's a family version of Fredholm operators. But to be able to define that, I need I need to talk about the Hilbert module coming from the action on the manifold. So whenever we have a locally compact group acting on the manifold M, one can define a CCG valued inner product over the compactly supported smooth functions on M by just translating. So given two functions on M, one can just translate one function by a group element and take the usual inner product. And as this group element changes, one get a function on G, and this function is the so-called G-valued inner product. And one can also define, one can also regard this C infinity function as a CG module under this convolution-like product. And by showing these conditions, one can regard one can really regard this C infinity function on M as a C infinity function on G module. And after doing the completion over this inner product, when see that when obtain Hilbert module over C star G, and we denote it by epsilon GM. And in a similar fashion, one can talk about sections of a vector bundle to obtain a Hilbert C star G module. But here I would like to only say one example, because this whole process is quite complicated, and I want to say an example in the case we cared about, the case when M is G mod K and G is acting on this base on the right. And if we have the spinor bundle given by this associate bundle to the spin representation, if in this condition, this module is just it's very simple. It is just L2G tensor S invariant under K. So this is very explicit. One can easily check that this right-hand side thing is a module over the reduced group system. And in any case,
does it also define a Hilbert module structure over the maximal group C-star algebra at the same time, or you have to?
One can do it with respect to maximal or reduced. It doesn't matter, this process.
Thank you.
Because my time is up, maybe it is a good idea to postpone this to the next time. But in any case, I want to explain a few words about the idea. The idea is that now we lift our problem in the non-compact case, in the Gmod K case, where the manifold is non-compact, the operator is not Fredholm, we can still view it as a we can still view it as a we can still do some similar process like this to view this operator as a Fredholm operator, generalized Fredholm operator with respect to the module over C star G. And by some Morita equivalence argument, one can argue that the K-theoretic index lies in K-theory of C star G. And after that, yes, after that, one can talk about Dirac induction by thinking about Dirac operator on a homogeneous space G mod K twisted by a homogeneous vector bundle. Twisted by a homogeneous vector bundle, which is this V. This V is G K so this V is a representation of K, and from that one can create a homogeneous vector bundle over G mod K and twist this bundle with the canonical Dirac operator on G mod K, and one can define a K-theoretic index in the K-theory, and this map gives us a morphism from representation ring of K to the K-theory of group C-star algebras, and that is known as the Dirac induction map. And Kohn-Kasparov conjecture states that the Dirac induction map is an isomorphism of abelian groups. And I'm going to say more about this next time. So that is all my lecture today. And here are some references I want to mention. So I talked about Dirac operators and higher index, and for Dirac operators, one can look at Olsen and Michelson spin geometry, and for higher index theory, one can look at Hickson and Rose analytic K-homology. And for the group theoretic part, if one wants to see how Dirac operators has something to do with representation theory, for today's lecture, I only recommend Pastor Dorothy, Tia Schmidt, and Kohn Moskowicz's papers. But more references will come up in the next two lectures. So that's all. Thank you.
Thank you very much, Hang.
Thanks.
Okay, there is one question that was lingering from the middle of the lecture. I postponed it to the end. So let me ask, came from the audience. So the agreement of Dirac on a complex manifold with the Dolbeau operator. The question was, do we need to twist the Dirac with the determinant line bundle to get Dolbeau, or is it already on the nose agreeing?
I think no. I think we twist determined line bundle to create some spin, to specify spin C structure, right? For Dolbeau operator, we don't twist the determined line bundle. But I should say, the two operators, the double operators and the canonical Dirac operator on the complex manifold, they are not necessarily the same, but they differ by some, they may differ by some lower order part, I think. They are not exactly the same, but they are the same in the context of in topologically they are the same.
Is that one of those they have the same principal symbol kind of thing?
Yes.
Mm-hmm. Okay, I think that helped. It's in the chat box, by the way. I think, yeah, this was, we weren't able to see the very bottom and the very top of your slides for some reason.
Maybe I should use a different software.
That for the next lecture, but that would be helpful slightly. Yeah, any questions or comments to Hang? Okay, there's a question. Could you perhaps recall how the Dirac operator twisted by a vector bundle is defined?
Oh, so the vector bundle, the sections of a vector bundle can be viewed as a direct segment of a free module, because of by Sayers-Wang theorem.
Your iPad is gone to sleep or something. Maybe you could bring the page back. I think you put it on the slide.
Should I see?
Did we lose the iPad? Okay, it's coming back. Yeah.
Where is it?
Slightly earlier. Yeah, here.
Yes. So this vector bundle V, we can find a complement vector bundle to make it a trivial vector bundle. And taking section, then have a direct sum of the sections equals to C infinity m to the n, which is a free module. And one can define a projection from this free module to this direct segment. We call that P. And on the right hand side, one can still talk about Dirac operator. Just act diagonally, because Dirac operator acts on each of C infinity m, right? C infinity m, and we have n copies of those. And to create this dv, one just compress this operator by p on both sides, and it will become an operator on p C infinity m n. But that is exactly this one, C infinity v. Actually, the official twisted Dirac operator is not defined like that. It is defined as follows. Find a blank page. So because the if one can express the Dirac operator like this, Then a twisted Dirac operator is in fact defined in the following way. Oh, sorry. Twisted Dirac. And this new connection is just we take an arbitrary connection on V, which I call nabla V, and create this new connection on the tensor of this bundle. And one can still talk about Dirac operator like that. That is the official definition of twisted Dirac operator, but that is the same as the one I defined using compression. The idea is that we want to avoid using connection because it's very complicated. Actually, in the context of representation theory, one can avoid that by saying that Dirac is just CPI, Clifford multiplication by PI and PI, where PI comes from the algebra. So in that sense, we can avoid connection, so which makes it easier.
Thank you. Any other questions to Hang? Was that six-term exact sequence argument relating the Fredholm index with the K30 index, was that at the end of Moscovici paper? There was something like that they were defining. I wonder if as a source it's coming from there or? I guess not. So you would probably get it, yeah, quickly if it was the case. Your voice is gone, by the way. I think the internet is acting up. Or is it me? I can't hear anyone now. Hang, I can't hear you. Can anyone hear me? Okay, so some people hear me, okay. All right, it looks like Hang's connection is not very good right now. Anyway, I guess it wasn't a great question anyway. So perhaps, okay, let's thank Hang again. Hang, thank you very much. And let's stop the recording.